Okay, so we're going to talk about a few things. First, a set of slides regarding the sensors and the actuators. And I will then talk about ADC, analog to digital converter. And at the end, I will briefly introduce the accelerometer and gyro chip that we're going to use in the next lab. So today we're going to look at what is a sensor and what is an actuator. We're going to look at what is sensor first. A sensor is a device that measures a physical quantity. So when we have this cyber-physical system, it interacts with the physical world. So there are a lot of physical attributes that we want to understand. Sound level, temperature, speed. So these are the physical quantities. You can think about that the sensor is an input, and we want to have some data that we can read from the physical world into this cyberspace. On the other hand, an actuator is a device that modifies a physical quantity. So you can use a device to drive your motor, drive your gear, or you can turn on the LED or turn off the LED, and you can have other physical quantities, physical attributes that you want to have impact or have effect on using a device. And such a device is an actuator. So as opposed to the input, now we are talking about actuator as an output. So we want to have some capability to write to the physical world. Not literally write, but to have some impact to the physical behavior of the system. Here's just a short list of the sensors. For example, cameras, image sensors, accelerometers measuring the acceleration, and gyroscopes measuring the rotation. And we also have strain gauges, which is to measure the pressure or the strain on the surface. And we have sound sensors, microphone. We have magnetometers to measure the magnetic fields, radar and LiDAR to monitor the distance, and also a variety kind of chemical sensors, pressure sensors, and switches. All these are different sensors. And for a modern car, there are a lot of sensors equipped, from parking assistance, brake assistance, traffic alert, lane departure warning, side impact, parking assistance, blind spot detection. So all these fancy systems on modern cars are enabled with sensors. It's important that we use these sensors to understand the physical surroundings, the distance between cars and between obstacles, between pedestrians and cars. So those are what we need to understand when we design and implement these subsystems in these modern cars. And in this particular diagram, we use two colors to illustrate some of the sensors are ultrasonic, and some of them are based on radars with active sound signals, radar signals. Also with the cars, we see here a lot of the systems or sensors that we have to have, and they vary based on their functionality and also their cost. For example, GPS can be used to track the location. It combines readings from different sensors, tachometers, and altimeter and gyros to provide the most accurate positioning. The cost could vary based on the precision you require. And ultrasonic sensors is to measure the position of objects very close to the vehicle, as opposed to LiDAR. So that's the light detection and ranging. That's to monitor the vehicle surroundings, road, vehicles, other vehicles, pedestrians, etc. And that's used to measure objects with a further distance. Visually, we need to use video cameras to monitor the surroundings, and nowadays we use deep learning algorithms to analyze these videos in runtime to understand the traffic light, to understand the moving vehicles and the pedestrians, and that's kind of enabling technology for the auto driving features in modern cars. On the top, I hope you can see this video. This shows a very early project. Basically 20 years ago, UC Berkeley had this research project that they modify the cars with sensors and write control software to implement this self-driving. You can see that in terms of just looking at the interface, this is rudimentary compared to the modern Tesla. But at that time, this technology was so advanced that they really took a lot of effort to modify existing vehicles, to equip those vehicles with sensors and computational devices. So you can see here antenna for GPS. They have this spectrum receivers, and a lot of sensors are mounted outside the car. Here you have a camera, and so these sensors enables the control software and to implement such a autonomous driving system. And on the top right on the slide, you see that's the Google self-driving car. It's much smaller in terms of the car, but the sensors are even more than the earlier project. But the main message here is that these sensors played a vital role in enabling such autonomous vehicles. The other project is also from Berkeley, and this is 15 years ago. This is I don't know if you can hear the sound. This is a big machine, the snow blowers used on highways. So these vehicles are different from the previous one. These vehicles are huge and they go slow, but they have to be very precise. So the distance from the snow blower to the rail of the highway has to be very well controlled. Okay, so gap distance is from 1 to 3 inches, because if you go over that, the chance that the vehicle will be damaged by colliding into the guardrail. This is the similar project. So what they want to show you here is the sensors mounted underneath the car, the truck. It's the front magnetometer arrays that they use to detect the directions of this blower truck. So this is where they keep the machine that runs the control software. It was a old platform running a QNX real-time operating system. A simple switch basically switch the truck to auto mode, and in that case, the control system will be able to manipulate the steering system based on the sensors reading. There's also guidance indicators, warning lights, etc. This is the actuator to implement the auto driving. So this part of the video shows this blower can be operated autonomously and keep a very fine distance between the blower with the guardrail. Yeah, very neat design. This is the sensor that was used on that blower truck. It's the magnetometer used to measure the magnetic field so that they can know the exact direction the truck is going. It's based on the Hall effect. This sensor works by charging a conductor here. That's a conductor, a piece of metal, and the electrons will go through this loop. And because of the Earth's magnetic field direction, it will induce a impact on how the particles, the electrons accumulation on either side of the conductor plate. So if the electronic field is this way, then the particles will be saturated on one side, on the other, basically further side of this plate. And that will cause a measurable voltage difference from the top to bottom. And based on the direction and the plate will be showing different current and magnetic field polarities. So this is essentially how the magnetometer works, and this one was used in that blower truck. Okay, so accelerometers. Yeah, because if people joining a little bit late, they will show up on my screen and I'll have to admit them. Okay. You will use accelerometers in many situations: navigation, orientation, drop detection, image stabilization, airbags. So the usage of accelerometers many places, and the most common design measures the distance between a plate fixed to the platform and one attached by a spring and damper. So if you imagine that we have a plate like this, and this is the fixed frame, and the movement part is the movable mass, which is connected to a spring and a damper that's not really shown here, but in the movement of this mass could be this way or that way, if you move this mass further, the spring will pull it back towards the center. If this moves too close to the spring, to the fixed frame, then the other direction of the force will push this mass away. So this platform could be in different orientation, but either way, this movement of the this movable piece will be along this platform, this direction. And the measurement is typically done by measuring the capacitance between this movable piece and the fixed frame. Based on the distance of these two pieces, the distance, they will produce different capacitance, which can then be measured. So that's essentially how we measure the acceleration in a given platform, in a given direction. There's a physical model behind this kind of design or this system. Based on Newton's second law, the force is equals to the mass times the acceleration. So we will be using this basic principle to calculate the acceleration. For example, the F could be Earth's gravitational force. And if you have this system vertically, let's say this moving direction is vertical along the Earth's gravity direction, then for this movable piece to balance, essentially that's going to be the gravity of this piece. So we can then use this Newton's second law to calculate the acceleration. To be more precise, this is the spring mass damper system that we can model using Newton's second law. And we have this mass represented with symbol M, and the spring constant K representing the kind of elastical, the property of the spring itself. And we use P to represent the position, the rest position, which is the neutral position, where this mass can sit with there's no movement. And the position of the mass will be X, which is a variable that will change from time to time. And the viscous damping constant will be the opposite force that will be pushing this piece away if it's get too close to the fixed plate. So what we can do is we have a few equations can be established. This force, F1 at time t, equals to this spring constant times the position, the rest position, minus the current position of the mass. And so based on how far this movable piece is from the neutral position, the spring will be generating a force to pull it back. So this is what essentially is describing that force. And this is the spring constant, and this is the displacement of that movable piece. And on the other direction, we have a viscous damping effect, which will be pushing the move piece away if it's getting too close. And this is calculated as the damping constant C, negative because it's the opposite direction. This x dot t, this is actually the change of the position in terms of time. So you can think about this as the speed of that movable piece. Okay? And Newton's second law, we can represent that using this equation here. These two forces together, one is the positive direction, the other one is the opposite direction because of negative sign. This force equals to the mass of that movable piece times the acceleration. So x 2 dots t, this is the acceleration, so the change of speed. Okay, this is effectively what we want to measure using the accelerometer. Now with this accelerometer, we can also measure the tilt of the device. The way we measure that is very simple. If you tilt this device to a certain degree, assuming that, let's say, from the vertical, we tilt this platform in this way with the angle to the horizontal line, there's a theta degree. And because this device will also have gravity that will be applied to this moving piece, so that gravity force, which is going down, will be can be represented using two axes. So one going this way, one going the other way, which is perpendicular to the platform. And the direction, the gravitational force applied in the direction of the this platform, which is the accelerometer's axis, must be equal to the spring force. So what we see here is the mass times the g gravity force, the constant will find out this angle using sine to get that portion of the force. That's the same as the first equation that we saw earlier, which is the constant, spring constant times the neutral position, subtract this current position. So the displacement from the neutral position. So given a measurement of this x, which we can have, in some way, and if you know this displacement, this distance, you can then solve this equation to find out the theta. And there's ambiguity of pi because you may tilt this way or the other way. So there's some ambiguity possible. So that was a brief explanation how accelerometers work to measure the acceleration. As we can see that there are some things we need to consider when we design or use accelerometers. First of all, it's difficult to separate tilting from acceleration. As we saw earlier that there's gravitational force can be applied if you have the platform tilt in certain degrees. Also, vibration will cause the accelerometers to have a lot of interference in finding out the displacement of the moving piece. The x could be impacted by the vibration. Also, in the previous model, we assumed the spring property is a constant k, and the viscous damping effect is a constant c, but those could be non-linear in the real situations. So the model could get complex. Also, if we want to use accelerometer to get back to find out the position, there can be some issues. What we show here is in order to find out the position, we essentially need to find out the initial position P0, so at the initial state, and then we do an integral on the velocity, this tau, this v tau, so the velocity, doing integral on a t, that will give you the displacement or the distance between the current position and the starting position. And to find out this velocity, we can use the acceleration to do the similar integral calculation. So we have a starting speed, and then we do a integral on the acceleration over t. Then that will give you the difference on the speed. And then using this difference and the initial speed, in theory, you can get the current speed. But because now you are doing 2 times of these integral computation, and any displacement, any bias in these measurement will cause this huge inaccurate estimate error on the position of that movable piece. So to resolve these issues, so in 1997, there's one PhD dissertation specifically on how to improve the accuracy of these micro accelerometers. And the design is called the feedback control, digital feedback control. And that essentially solved a lot of these issues and improved greatly the accuracy of accelerometers. And these designs have been implemented in the modern MEMS-based devices to create such accelerometer chips used in airbags and computer games and disk drives and wearable watches, all these applications. So that was the some history there. And this picture shows at microscope level how these MEMS devices are designed to measure such accurate accelerometer values. Okay, so that was the accelerometer sensor. Next 2 slides, we're going to look at the other sensor, gyroscope. Gyroscope is used to measure the changes in orientation. So when you change an object, you can rotate it in different ways. Essentially, you can think about there's 3 dimensions you can rotate, as we can see from the left side of the animation here. Traditionally, you can use optical gyros. That is to leverage the SAGNet effect using lasers. So on the right side of this diagram, we show the design in principle. We have a light source that will generate lights, and we have basically light beams going out from this way. And we have mirrors that's formed in this particular shape. And if there's no rotation, this light source will be reflected multiple times along these mirrors. And because there will be some light beams traveling in different directions, so that there will be interference. And such interference will be measured by some other sensors at this viewing screen. When you have this, several mirrors are rotating, the light travels at in one direction the distance will be smaller than the light travels in the other direction. And using this, it will cause the changes in the interference. And based on the changes in the interference, we can infer the rotation in that direction along that axis. Well, of course, people have been improved that using MEMS gyros instead of using optical. The second lab, actually, we're going to be using both the accelerometer and gyro to build a game. I can talk about that next class, but just give you some teaser to get excited about. Next sensor is the inertial navigation system, or sometimes you can see the terms IMU, internal inertial measurement units. These are combinations of things. The inertial navigation system combines GPS for initialization and some error checking periodically. Also, in this system, it has gyro that will measure the orientation, and it has 3 axes typically. In addition to the gyro and GPS, you can find accelerometers for 3 axes, and it integrated for positioning after the correction and for orientation. Such systems are designed in very high accuracy. The typical drift for the system using aircrafts can be 0.6 nautical miles per hour or tens of degrees per hour. They have to be calibrated from time to time, and depends on the actual applications. You may need to find more accurate system than this. It really depends on the application to understand whether you have sufficiently accurate system measurement sensors for your system. The next sensor is string gauge. String gauge is for measuring the growth of a crack in masonry, foundation, or other surfaces. And with this kind of sensor, you will be able to detect the tiny movement over a longer time period to understand how these objects, the surface, have deformed or changed their shape. The tensions will cause the area between these sensitive patterns to change. As a result, that will change the circuit's resistance. So by measuring the resistance, you can understand how these surfaces change their shapes, change their formation.